Hello everyone, welcome to the course Electromagnetic Theory. My name is Pradeep Kumar K and I am a faculty at the Department of Electrical Engineering, IIT Kanpur. So today we will first look at what is electromagnetics. Now before one starts studying a subject, one has to know what is that subject that one is studying, and then that essentially leads to the second question, that why should one bother studying this course. In other words, where does electromagnetics fit in electrical engineering curriculum? We will also discuss the syllabus, topics, course plan and the textbook that I am going to follow in this course. And we will begin by first defining electromagnetics in its broadest terms. Electromagnetics is essentially the study of interaction of fields that are generated by time varying charge distributions and currents. Now this definition does not probably mean anything to you at this point, because the questions that you can immediately ask, and that would something that you would ask, is what is a field? We said that electromagnetics is the study of interaction of fields that are generated by possibly time varying charge distribution and currents. So the question that should naturally come up is, what is a field? Then how are these fields generated by charge distributions and currents? How does a particular charge configuration generate a given electric field or magnetic field? And how would a current distribution generate a magnetic field or an electric field, and then what is the interaction between these two fields. So this is broadly the scope of this course. We will be looking at all these questions in greater detail. The reason why we are looking at electromagnetics is that if you complete this course successfully, this is a foundational course for your advanced courses such as microwaves, radar, antennas, integrated optics and fiber optics. So without further ado, let us just warm up to electromagnetic theory. Most of us are coming from circuit theory background, and this course is usually taken by electrical engineering, electronics and communication engineering and telecommunication engineering students in their second or probably third year of their curriculum. So you have all been exposed to circuits, you have done couple of courses in circuits, filters, networks probably, and you might be wondering, what is this electromagnetics that one needs to study? Isn't circuit enough to understand whatever that is there in electrical engineering? So the goal of the next few minutes is to show you where electromagnetics is necessary to be invoked, and why circuit theory in certain situations fails to give correct answers. To do that, let us first look at this particular circuit here. We have a signal source. This signal source could possibly also be a battery, and then there are two long pair of wires which I am showing in this orange color. Okay, these wires can be assumed to be ideal. Now at some time t is equal to 0, we are going to connect the two wires to the signal source. Now we ask, for this circuit, what will happen? Now one can possibly come up with different answers. So the first answer that one would come up is nothing will happen. Then one can say, no, current will flow for some time and then nothing will happen. One can also say that the problem is not completely defined, in the sense that I have not told you what is the length and the shape of the wire. I have also not told you what is the frequency of the source. Would all these things matter? Let us look at each of these responses individually and we understand where the limitations of circuit theory lies. From our circuit background, we might first think that, well, circuit is not closed, which means that there cannot be a current flow in the circuit. Whatever the voltage that is there at the source end will directly be available at the load end, right? The open circuit voltage of the source will be equal to the voltage at the load end. Now frequency of the source and length of the wire does not really matter to us. Now that is what circuit theory would tell us. So in a sense, if you are a circuits person coming purely from the circuit background and not knowing anything about the electromagnetic field theory, you might really be seeing this physical situation in which I have a voltage source, I have a switch which is closing at t equal to 0 and a pair of wires as something like this, right. The important point to note is that in circuit model of this physical scenario, the length of the wire and the frequency of the source do not matter. Now from our earlier physics course, we know that a battery is essentially source of electrons and ions probably, and if we connect that to a pair of electrodes which are made up of metal, then there must be some amount of charging that happens. So there is a charging, and this charging current must flow for some time until the wires are charged. And so the question is, how exactly does this, what process causes this charging of the wire? what is the exact voltage waveform? Does that depend again on the frequency of the source? So, these are the questions that cannot be answered from the circuit paradigm, because circuit theory does not consider these issues. So, we need to know something else beyond circuit theory to answer these questions of the charging process, the shape of the current waveform, and for how long that charging current would flow. Now, let us also look at a shape of the wire. I mean, this is something that you can do in your lab or in your house, provided you substitute certain components over here. You take a signal source, or you can take a battery, does not really matter. You take a switch, and then the two long pair of wires that we had considered, you take one of the wires and sort of bend it over. Okay? There is no necessary that it has to be bent in a square form, but you can just bend it in any way, but you make sure that you have bent it sufficiently. Okay? And then you connect a resistor at the other end, and then hook up the output of the resistor to an oscilloscope. So, you can clearly see that oscilloscope is connected to the resistor end, and what is that we would obtain at the oscilloscope from this particular physical scenario? Well, going back to circuits person, as we have already said, this length of the wire, just because it is bent, does not really mean anything. The voltage after switching at this point will be exactly equal to the voltage across the resistor. So, the voltage would come across the resistor, and you would expect that the same voltage should be displayed on the oscilloscope. If it is a sinusoidal waveform, you would expect to see a sinusoidal waveform on the oscilloscope. Okay. However, as you start increasing the frequency of the source, it turns out that at sufficiently high frequencies, this wire will actually cause the voltage across the resistor to drop to 0. Now, this is something that one cannot understand from the circuit point of view, because for us, for circuit people, this bent wire is equivalent to a straight wire. There is no reason why the shape of the wire should influence the output voltage across the resistor. Okay. So, for an electromagnetic person who will study this course, what he or she would see is that this same bent wire plus this other unbent wire or a straight wire at low frequencies looks like a inductor, okay, and at very high frequencies looks like a transmission line. Okay. However, both inductance and transmission line are concepts that are not actually developed from circuit theory. In circuit theory, if you remember, we just are given that we have an inductor, we have a capacitor, we have a resistor, and we are not told how we exactly calculate these things, right. So, what is inductance and how do we calculate it requires us to go beyond the circuit paradigm to really answer these questions. Now, let us do this exercise in which we take the wire, we make it straight, but then we cut the wire into two halves and then replace the wires at the end by two metal plates. One can think of large metal plates, and then we replace this one. Now, we apply a certain voltage, from a function generator, and what do we expect to see at the output of the resistor? Clearly, there is no continuity of the wire between the two plates over here, because the plate is broken. There is nothing out there that will allow the conduction of electrons from one wire to another wire. However, we do know that this situation is exactly that of a capacitor, which again comes back to the same question, just what is capacitance and how do we calculate it? We know that the current will be continuous, that is the current that is going through here must be coming out as the same current. Voltage will be different phase, but the current will be all the same phase. So, the current that is flowing here at one plate must also be the current that is exiting the other plate. Now, what exactly goes on in between the two plates is something that electromagnetic theory will help us understand. Finally, we come to the length of the wire. Okay, in circuit theory, again, length of a wire or an interconnect between two gates or two circuit elements does not really matter. It could be any length, but what we assume is that the voltage at one end of the wire or the interconnect is exactly the same at the other end of the wire, right. So, there is, if you can take the length of the wire to be say 1 kilometer, 2 kilometer, 3 kilometers, that does not really matter. Whatever the voltage that is over here should be the voltage here, at least that is what the circuit theory would tell us. So, if you apply a sinusoidal voltage that is shown over here, right. So, please note where the maximum is occurring. At some t is equal to 0 point, the maximum of the voltage source is going through a maximum. However, what you observe on an oscilloscope that you put at the far end or at the load side, if you would think, is that the maximum does not really occur at t is equal to 0. It occurs after a certain time, and this time is L by V, right. So, this is actually confusing to us, that is for circuit people, because the wire length should not matter. The resolution of this paradox is that a long wire actually causes delay, and voltage and currents are not really the scalar variables that we have thought so far, but they are rather waves, and a wave that would experience a certain time delay of L by V when it propagates with a phase velocity of V. Now, you might not really understand all these concepts at this point, but just keep in mind that whenever you are connecting a source and a load which are separated by a long distance, there is some time delay involved, and this time delay is not taken into account by circuits, whereas this is explicitly taken into account by electromagnetic theory. Therefore, if you actually take this scenario of having a source at one end and a load at say 3 or 4 kilometers at the other end, then you will clearly see that there is a certain amount of delay in transferring the voltage from one point, that is at the source, to at the load side. Now, this is something that circuit theory does not tell you. That is the reason why we call circuit theory models as lumped parameter models or lumped circuit modeling. A lumped circuit is one in which one can simply neglect this time delay, and therefore, there is no change in the voltage waveform that is at one end to at the other end, and in other words, the length of the wire does not really matter. Takeaway from the previous slide is that there is a certain time delay whenever you have a wire that is connecting two circuit elements, and this delay can be ignored in the circuit region because of various reasons. We will actually talk about all these reasons in a later time, but this delay is not predicted by the circuits, whereas electromagnetic theory will incorporate this delay. So, we have to consider the time delay, and if this delay is because the current on the wire is not really just independent of the distance, but it is actually a function of the length of the wire. That is, if you take the direction of the wire in which you have connected as the z axis, then the voltage at any point on the wire would actually be a delayed version compared to the voltage at the beginning. Okay. So, this phenomenon of time delay and thinking of current as a wave is not predicted by ordinary circuit theory, and it cannot even deal with such phase delay effects without explicitly involving this phase delay into circuit paradigm. So, what happens at very high frequencies is that the wires start acting like transmission line, where the phase difference or the phase shift between the voltage at the source end to the voltage at the load end becomes an appreciable fraction of 360 degrees. Okay. When it becomes an appreciable fraction of 360 degrees, one has to explicitly take into account the delay that is there between the source and the load. Okay. So, that leads us to the question as to what is a transmission line and how do we analyze this transmission line. Now, you might ask, well, so far we have talked about circuits and electromagnetic theory, and we said that there are situations where circuit theory does not give you correct answers, whereas electromagnetic theory will give you correct answers or correct predictions. So, what? I mean, why should we be bothered about this electromagnetic phenomenon? Well, to consider a device which is very close to us, such as a computer or a cell phone, each of these devices which essentially perform computing stuff, they actually contain millions and billions of logic gates, and these logic gates are all switching at very fast, very high speed, and the gate switching time, that is, if the gate goes from high to low or from low to high, those switching times are getting shorter and shorter. Now, you can have fast gates which switch in the order of 100 picoseconds. Now, if the interconnect is such that the delay of the interconnect itself is about 200 picoseconds, then the voltage, while this gate is switching from logic high to logic low, the same voltage will not be available at the same time, and then the second one will switch after a certain time. Now, when you have such interconnects connected, you have these different elements or logic gates connected together. If the difference between the two interconnects is large, then the voltage, because of the same source, will not be the same at one logic gate compared to the voltage at the other logic gate, and therefore, this might lead to inconsistent results and completely inaccurate results. The correct model of this scenario is to treat this as a logical element, whatever that you are considering, and this is another logical element which is switching. However, the space between these two, which is connected by a piece of metal or a wire, and on a VLSI these are known as interconnects, as transmission lines. Now transmission lines are characterized by several characteristics. One of the most important characteristic of a transmission line is that of its characteristic impedance. So here you can see that the characteristic impedance ZC is given to be 124 ohms, and the time delay of the transmission line or the interconnect is given as 0.3 nanosecond. And if this is the source voltage, you can see that the source is switching from logic low, which can be represented as 0 voltage, to logic high, which is 5 volts, and this is switching from logic low to logic high in about 0.5 nanoseconds, okay, and thereafter it is constant for about up to 10 nanoseconds, and then switches back to logic low at again with an interval of 0.5 nanoseconds. This is at the source end. Now if you take this source end, that is the voltage at this point, and see what is the voltage that you would observe here at the load end, you would actually see something like this. There will be ringing effects. The square wave is just for the comparison. So you will see overshoot and you will see undershoot. Now this is something that one would not expect if you go simply by the circuit theory. So in order to obtain this correct output, or in order to predict this one has to replace the interconnect by a pair of transmission lines, or actually a single transmission line, okay. So we model this source by a voltage source with a resistance and the load by say capacitive load, for example, and then this piece of wire which is called as the interconnect that connects the two logic elements as a transmission line. Now you might ask, how do we calculate this transmission line characteristic impedance, what is a transmission line, and how do we calculate this time delay Td, and what do these Zc and Td variables have any effect on the load voltage. We know that there is a load which is not exactly equal to the source, but how is this voltage at the load related to the transmission line effects? Again we have to go back to electromagnetic theory to understand where these parameters are coming from. For example, if you want to calculate the characteristic impedance, if you remember the impedance definition is voltage divided by current. However, we have just seen that voltages and currents are not just numbers, they are dependent on where you are measuring them, right. So this voltage and currents are more accurately defined in terms of electric fields and magnetic fields. So voltage is defined in terms of the electric field and current is defined in terms of magnetic field. And when we excite a transmission line by a voltage and current, we say that electric and magnetic fields are generated. So here you can see that electric fields are generated and the current is generating a magnetic field. And then to obtain the characteristic impedance, we have to relate the voltage V to the generated electric field, we have to relate the current I to the generated magnetic field. And one cannot do so, that is one cannot obtain or one cannot understand the electric and magnetic fields unless one studies electromagnetic theory. Electromagnetic theory tells us how voltage is related to the electric field, how current is related to the magnetic field, and these relationships in turn give us the relation for a resistor, they also give us relationship for an inductor and a capacitor. This is how we actually can model the physical phenomenon that we have so far discussed. Now I think this is a right time to just summarize what we have done for the first 20 minutes over here. Wire is more than just a wire, right. What we see as a wire at low frequencies and at the circuit level is not just a wire, because it can act as an inductor, it can act as a resistor, it can act as a capacitor, or in a worse scenario it can act as a complicated or a complex circuit that can be modeled as a combination of resistance, inductance and capacitance, okay. It can also act as a transmission line when the frequency of the source is very high and there is a relationship between the length of the wire and the frequency of the source, we will discuss that later. But again the point is that a wire is not just a wire, it exhibits lot of secondary effects such as inductance, capacitance and resistance and all these combinations, and we need to understand electromagnetic theory to be able to account for these secondary effects. Now secondary effects are very important when you are designing say high speed digital systems or you are designing an RF circuit. Unless you understand these effects, your designs will not probably work in the correct way or as you have intended. The reason why this electromagnetic theory has to be studied is because the ordinary circuit theory cannot account for these effects, whereas electromagnetic theory can successfully analyze these effects, okay. It is not just circuits where electromagnetics comes up often, it is also that electromagnetics opens up a wide array of topics that one can specialize in, that is one can find applications of electromagnetics in. Now, you must certainly have heard about fiber optics, and optical fibers are the ones which carry 99% of the world's traffic, right. So, all the high speed advantages that, I mean, all the high speed data transmission that we are now familiar with is mainly due to the optical fibers and the ability of optical fibers to carry this large amount of data with very little attenuation. Now, how exactly data, which is actually an abstract quantity or a voltage or a current, in the abstract quantities mapped onto voltages and currents, how would they be excited inside an optical fiber, how would they travel inside an optical fiber, is something that electromagnetic theory will tell us. It tells us that light, which is appropriately modulated by the source that we are by the data that we want to transmit, actually goes through as modes inside a fiber, and these modes would travel. Okay. So, there are these different modes which I have shown. These modes have certain numbers and certain superscripts, they have certain letters. You do not have to worry about these numbers or superscripts, these are just the different types of light distribution inside an optical fiber. To understand this, one needs to know electromagnetic theory. One views an fiber optic cable or an optical fiber as example of solution of Maxwell's equation, and whatever that comes out of the solution are called as modes, and these modes are essentially the electric and magnetic fields of the light that are distributed inside the fiber. Okay. So, in order to know that, in order to know what is Maxwell's equation, we have to study electromagnetics. Now, you might go to antennas or radars, where in radars antennas are one of the major components, and in wireless communications antennas are there everywhere, right. Without an antenna one cannot have a wireless communication possible. Now, to understand how I have shown different types of antennas over here. This is a simple dipole antenna, this is a horn antenna, this is a this is a reflective antenna, and this is a microstrip antenna. The question is, how exactly does this antenna, the dipole antenna, differ from a horn antenna or a pyramidal horn antenna, and how does that differ from microstrip antenna? What parameters makes the radiation pattern of these antennas be different, and how do we analyze them, and how do we make use of these radiation effects and radiation patterns, is something that again that electromagnetic theory will tell us. Okay. So, just to give you an overall perspective of electromagnetics, you can, I am just going to list up here, you can see this later. Electromagnetic theory opens up vistas in optics. You have optoelectronics, which is concerned with how do you fabricate a waveguide, how do you analyze a waveguide, how do you analyze a light modulator, how do you couple light from one waveguide to another waveguide, and how do you generate integrated optical components, how do you understand fibers, and so on. If you also want to understand lasers, photodetectors, photodiodes, again you have to understand them with certain help from electromagnetic theory. And if you want to understand the nonlinear properties of light propagation or linear properties of light propagation inside a fiber as something that you would find in optical communications, you again require electromagnetic theory. If you go to communications and you want to understand different channels such as air channel or a copper cable or a fiber or ionosphere for radio wave propagation or for radio astronomy, you again have to know electromagnetic theory. Now, you also need to know electromagnetic theory for circuits to give you a philosophical justification. See, historically electromagnetic theory was developed first, then the simplifications of electromagnetic theory for circuits was formulated in terms of Kirchhoff's laws of KCL and KVL and Ohm's law. These are fortunately very special cases of Maxwell's equations, where we can neglect the time delay between any 2 points in a circuit. Okay. So, electromagnetic theory gives you the reason why KCL and KVL should be true. They are not true by themselves, they are only special cases of electromagnetic theory via Maxwell equations. You can go to RF and microwaves, where you will be designing microwave components, that is components on an integrated circuit. You will be doing measurements such as VNA spectrum analyzer, VNA stands for vector network analyzer. Microwave circuits, you might be designing them to make an RF transmitter, an RF receiver, or a radar transmitter or a radar receiver, and many other cases, essentially with frequencies typically over 2 gigahertz and above. Again, to understand microwave circuits, you need to know electromagnetic theory. Of course, there is an entire area of microwave engineering which deals with active and passive microwave devices. Again, electromagnetic theory forms the mainstay of understanding these different fields. One can also go to its different area altogether called high voltage, where the idea is to design dielectrics we will study what dielectrics are later for very high voltage applications. We are talking about kilovolts or tens of kilovolts of voltage out there. Electromagnetic theory is also used in dynamos, generators, which is typically called as low frequency electromagnetic design. Electromagnetic theory is also used in biological systems, sometimes called as bioelectromagnetic phenomena. Finally, from electrical engineering perspective, antennas are one of the major applications where we are going to require electromagnetic theory. What we study there is what is an antenna, how do we analyze it, what are the different types of antenna, what are the different types of measurements that one has to perform on an antenna, and how are they justified by electromagnetic theory, radio astronomy and radar systems. So, I hope that an entire this one that we have talked about so far gives you a basic idea that electromagnetic theory is very important, it is indispensable to electrical engineering, and a good knowledge of electromagnetics will take you far and wide into different areas of electrical engineering. Okay. So, with this background as to why one should be bothered about studying electromagnetics, let us now look at what is the course plan and some of the suggested textbooks, and then start discussing electromagnetic theory itself. The course plan goes something like this. The course plan actually starts with static electric and magnetic fields, where we briefly discuss Coulomb, Gauss and Ampere. We also discuss how to calculate capacitance and inductance. Remember, I talked about capacitance and inductance of elements, and how do we calculate those in capacitance and inductance of physical systems is what we will deal with here. Then we go to electrodynamics, where we will be studying Faraday's law and complete the electromagnetic model by looking at Maxwell's contribution, which is called displacement current. And we will also discuss Maxwell's equations, and we also need to understand something about boundary conditions. The subject of boundary conditions will come up even in static electric and magnetic fields. However, when we complete the electromagnetic model, the boundary conditions will undergo a small change, and we are going to discuss about that. Then we come back to transmission lines. So far the two topics that I have shown here, static electric and magnetic fields and electrodynamics, are what you can say as building up to electromagnetics, building up to Maxwell's equations. Thereafter one has to apply those Maxwell's equations to physical scenarios to really make use of Maxwell's equations in designing some systems. Okay. So, those systems which are useful to us. So, the first system that we are going to discuss is transmission line. In transmission line discussion, we will initially forget everything about Maxwell's equation, and then we still cling on to voltages and currents. Now, this might sound very suspicious, like so far we have built up ourselves to Maxwell's equations, and thereafter we have sort of completely forgetting. I mean, I am saying that we will forget Maxwell's equation and still deal with voltages and currents. The reason why we do this is that transmission lines are an example where they are in between the static and the completely dynamic scenarios. Okay. So, one requires, one can get away by changing the voltage and current from scalar quantities into waves, and then talk about transmission line. So, it is kind of a bridge that you can build from Maxwell's equations to circuit theory. Okay. And that is what we do first, and the reason why transmission lines can be done, we will see the reasons later, is that this is applicable when the circuit dimensions is in the order of wavelength. If the circuit dimensions are very high compared to wavelength or very low compared to wavelength, you have two different models. We will discuss all this later. So, transmission lines are where we are still trying to understand that theory in terms of currents and voltages, because currents and voltages, let us face it, are something that we all know pretty well. However, when we come to the subject of waves, we cannot continue to ignore electromagnetic nature. So, we will start by looking at simplest solutions of Maxwell's equations, which are plain electromagnetic waves. It is at this point that we will show that light is also an electromagnetic wave, and whatever we study in terms of EM waves are directly applicable to light. So, electromagnetic waves and their properties is what we are going to study. We will then look at what happens if light or electromagnetic wave approaches a boundary. So, when you have something approaching a boundary, what happens to that electromagnetic field? So, that is something that we are going to look at. Will the field just penetrate the boundary, or will it come back from the boundary? How, if it comes back, how much it is coming back, and if it penetrates, how much is it penetrating? These are the questions of reflection and refraction. We are going to see where this, how to describe this phenomenon using electromagnetic waves. Finally, we will start looking at other applications of electromagnetics, the application that we will look at, a waveguide. As its name suggests, a waveguide is something that guides a wave along a certain direction. Okay. While transmission lines also guide waves, they do not enclose the electromagnetic waves between a boundary, whereas a waveguide will enclose all the waves inside a boundary. Okay. And that is why we call this as a waveguide. We will also see some justification of transmission line equations. Remember that in transmission line equations, we simply forgot everything about electromagnetic theory, but we have not really forgotten, we have simplified Maxwell's equations, and we will see how that simplification comes up when we look at waveguides and we understand that transmission line is also a waveguide, albeit of a different nature. Okay. We will also consider the more popular metallic and dielectric waveguides, and finally we will look at radiation, which is electromagnetic radiation through an antenna. We will not have too much time to discuss all the aspects of antenna, we will only be looking at the simplest of those, called a dipole antenna. Okay. So, here is the textbooks that I am going to use for this course. The primary textbook that I am going to use is Engineering Electromagnetics by William Haight and John Buck. This is, I think the current edition is 8th edition, but you can read up any edition from 5th to 8th. The topics have not really changed much. The recent editions have incorporated extra material on waveguides and transmission lines. So, you can pick up any edition after 5th, and this is what we are going to follow. I am going to follow 6th edition because that is what I have it with me. We will also use a couple of other books for references. One of them is called Electromagnetics with Applications by Cross and Flesch, and Electromagnetic Waves by Stalin. Okay. This Cross textbook is interesting in the sense that it talks about theory less, but it includes a lot of applications. So, if you are someone who wants to know where electromagnetics is being applied after every concept, you can consult this reference book. We will of course be discussing about the applications of electromagnetics as and when time permits to us.